Okay, well, we'll discuss it later. I think it's
Yes.
time to begin. So now today's speaker uh, is Professor Raffaele Vitola from the University of Salento. You see the title. So, Raf, you are welcome. Please begin.
Thank you very much, Joseph, for your kind invitation to deliver a seminar. And today I will speak about some aspects of WDV equations which are of interest typically for mathematical physicists. Okay, so the work is joined with Stanislav Opanasenko. And so I will speak about what are WDV equations. Then I will speak about transformation of WDV equations into evolutionary systems, because with evolutionary systems you have a powerful theory to deal with integrability, to deal with Hamiltonian formalism, and so on. And I will give some examples in low dimensions there, and I will speak about the general results, and here general means for any dimension, and general conjectures that we formulated during our research. So initially there will be a bit of superposition with the previous talk that I delivered here, I think, well, some months ago. So the equations, I use the presentation of Boris Dubrovin in the Encyclopedia of Mathematical Physics. The problem is to find a function of capital N variables, independent variables, and this function fulfills the following axioms. First of all, whenever you have a derivative with respect to T1 is a special variable. In a third order derivative, the result is a constant matrix, which is symmetric, of course, and it is this eta alpha beta. We also require that eta alpha beta is a non-degenerate matrix, so the determinant is 0, but we do not require anything about the signature. And then with the inverse of the matrix eta, you can lift one index in the third order derivative of f and obtain an indexed family where one of the indices is upstairs and the other two are downstairs. And you want these to be the structure constants of an associative algebra. This is a quadratic equation, and it is called associativity equation. And this is will give rise to the proper equations that we are going to study. Then you have another axiom. So you reduce the previous equations by requiring the quasi-homogeneity of its solutions. This requirement can be used or not. In our talk, it is not so essential. It is essential if you are studying, for example, integrable hierarchies and some physical problems, like in string theory in the initial formulation, it was essential. Okay, so if E1 En is the basis of R capital N, the associative algebra, which is defined by the triple derivative of f with the lifted index, acts in the way that you see here in the last displayed equation. And the first variable T1 plays the role of a unity in this algebra. So it's an associative commutative algebra with unity. It's commutative because the matrix eta alpha beta is symmetric, so the third order derivatives are symmetric with respect to the order of derivation. Now, I want to give some motivation to the study of WDV equations in themselves. The origin is in topological quantum field theory, so basically string theory. Now you can believe or not to string theory, but the point is that after they have been introduced by theoretical physicists, what happened was that people started to discover them in many other contexts. So it's interesting to study WDV equations even if you don't believe in string theory or are not interested in string theory. Then, so some mathematical developments were, well, the most important ones were by Kontsevich and Manning, who found a connection between solutions of WDVB and Gromov-Witten invariance. And this is illustrated in a, how to say, popularization paper by Ian Strong. You can find the link here. Of course, after the talk, I will make the slides available to everybody. Let us see something about the correspondence between solutions and the integrable hierarchies. In the famous paper, Geometry of 2D Quantum Topological Field Theories, this is explained. There are a lot more connections. And de Brovin introduced the concept of Frobenius manifolds. A Frobenius manifold is found after a solution, quasi-homogeneous solution of the WDV equation. This is explained also in a paper which I like, which is by himself, by de Brovin, Flat Pencils of Metrics and Frobenius manifolds. And a summary of his results can be found in Encyclopedia Mathematical Physics. Then some recent research. WDV equations can be found in supersymmetric quantum mechanics. As you can see, the Journal of High Energy Physics has a lot of papers about WDV equations. Then you can see that, again, topological quantum field theory is not died. It didn't die. So there is still some research activity on it. And then proper string theory, again, Journal of High Energy Physics, supersymmetric gauge theory, topological recursion. Here, this subject is very, very close. It's a bridge between mathematics and physics, where you can find certain quantities that physicists that are important for physicists to be important also for algebraic geometers, in particular those whose main business is numerative geometry. And the topological recursion framework has been laid out by Reinhard, Chekhov, Corentin, and it was about, now it's almost 20 years. And a very, very recent instance where WDV equations appear is the study of superintegrable systems. Superintegrable systems are those where the integrals of motion are abundant, 2n-1, where n is the number, the dimension of the system. And there is this recent paper that was published containing WDV equations whose solutions identify Hamiltonian systems which are superintegrable. So WDV equations are an interesting mathematical object, and there are reasons to study. So now let us go more in detail into the equations. S, alpha, beta, gamma, nu is the way we indexed the equations. There are many such equations, but there are a lot of symmetries in this indexed family. There is also something very important to observe. Since we made a requirement on the third order derivative of f, which contains at least one derivative with respect to T1, the requirement is here, just for your memory, then we can state that the function capital F is completely determined as far as its dependency on T1 is concerned, up to second degree polynomials of T1. But second degree polynomials are totally non-important because you see that the equation contains only third order derivatives, so they just disappear in the definition of the equation. So this is a gauge which is always there. So this is the aspect of the the unknown function capital F, and you can see that the proper unknown is relegated to a function of capital N minus 1 variables, this small f. So throughout our investigations, the unknown in the WDV system will be this small f. Now, let us remind what is a Hamiltonian PDE, but just in this slide, because we do not need more than this definition. So if we have an evolutionary system of PDEs, so a system of the form UIT, where UI is the dependent variables, an arbitrary number. UIT is equal to a certain function of the dependent variables, the independent variables, plus the derivatives of the former with respect to the latter, and only x derivatives. So here we are speaking about the system where the unknowns are as many as you wish, the dependent variables, but the independent variables are just 2. So if you have a system of this form, if the right-hand side of the system can be put in the form that you see here, so Aij with J contracted summed with the variational derivative of certain Hamiltonian density, then the system is in Hamiltonian form whenever A defines a Poisson bracket. In order for it to define a Poisson bracket, you have to require certain differential equations on its coefficients. Basically, A is a differential operator whose coefficients depend on in principle, also independent variables and derivatives of dependent variables with respect to the independent variables. In this context, such a differential operator is a differential operator in X only, not in T. So this is a Hamiltonian PDE, but you can see that the form of the WDV equation is quite different. We can go back one page. The form of the WDV equation is quite different with respect to the form of an evolutionary system where we have this notion in quite a clear way. So we would like to find a way to transform WDV equations into evolutionary system, which is something that it was not done by me, it was done by other people. First of all, Mohov, then Mohov, Ferapont, and so on. I will illustrate this, and I will try to generalize the results to arbitrary dimension. Solution of WDV equations, for example, every solution gives rise to a bi-Hamiltonian system of PDEs. This means that we can form a couple of Hamiltonian operators, as in the previous slides, just from one particular solution of the WDV equation, provided we have, first of all, distinguished, here it's not written, distinguished homogeneity degrees, d1, dn, mutually different. Then we set C, delta, gamma, beta, this constant, this, how to say, this function here, this is an index of family of functions. And by this family, if we write down Gij1 equals this expression, Gij1 defines a differential operator in this way. This gamma, capital gamma, is the Christoffel symbols with one lifted index of the contravariant matrix G1. And the two operators are compatible. So these two are two Hamiltonian operators, and they are compatible. So every solution which is quasi-homogeneous with distinct homogeneity degree of WDV equations gives rise to a bi-Hamiltonian system. Bi-Hamiltonian system means automatically integrable system. It's an integrable dispersionless system of the form UIT V equals Bij Ujx, sum in J. Okay, but then there are applications to enumerative geometry. For example, in the case capital N equals 3, we fix eta in the following form. This means, in the context of enumerative geometry, that we are dealing with the projective plane, and we can get a recursive formula for the dimension of the space of algebraic curves of degree n passing through 3n-1 generic points. And this is a famous formula which was obtained by Manin and Kantsevich. And this tells you what could be the interest of the WDV equations. In capital N equals 3, this is the first dimension in which WDV equations are non-trivial, and you have only one non-trivial equation. The other equations are trivial. But then the number of equations increases exponentially with the dimension. And in capital N equals 4, we have 6 equations and so on. So generally speaking, as a general feature of WDV equations, they are an overdetermined system. Now, let us see what is the generic form for arbitrary eta in the lowest possible dimension where the system is non-trivial. We have a single equation. The unknown is a function of of 2 independent variables, and the expression is here, it's written down here. Just remember that when you see eta in upper indices, this is the inverse of the matrix eta, components of the inverse. And then we can introduce, we want to transform this equation, which is determined, the only case of WDV which is determined, into a quasi-linear system of the first order. According with the terminology of Dubrovin and Novikov school, it's a hydrodynamic type system. So we introduce the compatibility conditions for third-order derivatives which contain at least once the letter x. So we choose
Raphael, I'm sorry. And what is V in the last line?
It is in the next slide. It is in the next slide. So it is here. I will show you. It is here, but I am going...
I see. I see.
Yes.
Okay.
So,
yes, thank you.
Yes. So we introduce 3 dependent variables, U1, U2, U3, and they are all the third order derivatives, so small f, where you have at least one derivative with respect to one selected independent variable. Which one is irrelevant, because the same geometric phenomena that we will find for x, we will find for y in this case. But this is a general theorem. I will give the statement later on. Now let us see the example. In this example, we have the following compatibility conditions. So U1y is equal to U2x. This is easy because you take an x derivative here, it must be equal to a y derivative here, and so on. But in the case of the third compatibility condition, you replace f y with using the equation. In other words, you restrict these compatibility conditions to a prolongation of WDV equation, first prolongation. In particular, this WDV equation, you make it explicit with respect to one variable. This is important because in dimension 4, we will see that this is a key idea. Making the WDV equation explicit with respect to f y means that we have f y equals to n over a denominator. This denominator is a linear form, as you see, in the dependent variables. And we have capital N, which is an expression, a quadratic expression of the dependent variables. So it's a rational function. So we have that our single equation has been transformed into a hydrodynamic type system where the fluxes of conservation laws, where the fluxes are rational functions. Okay, another important remark is that solutions of one in one set of coordinates of WDV equations are in bijection with solutions in the other set of coordinates. So if you take a solution in letter F you can obtain a solution in letter U1, U2, U3, and the other way around, up to second degree polynomials of the independent variables. This was observed, okay, by probably I read it in a paper by Sergei Agafonov many years ago, but it is not known, even if it is very likely, if this continues to hold in higher dimensions. So, but now let us discuss the Hamiltonian formalism of that particular first order quasi-linear system that we have seen. WDV system, WDV equations in the form of a system. What we can consider as a candidate for Hamiltonian operator is, how to say, normally one looks for simple operators, but in this case, so simple operators, one naively thinks that the simplest operator is the lowest order one. Unfortunately, here it is not the case. The simplest operator is a higher order operator, and in particular, we will show that all WDV systems in the form of hydrodynamic type systems are endowed with the third order operator in the form that you see in the last displayed equation. So this is a homogeneous operator of degree 3. This class was introduced by Dubrovin and Novikov as a class of operator which transform nicely under the viewpoint using point transformation, so transformations of the dependent variables. The point is that this transforms nicely also using projective transformations, and this was something striking. And indeed, this operator corresponds to a projective variety. We will see. So this theorem was, okay, indeed, the theorem in a special case of the simplest possible choice of matrix eta was first stated by Mohov, Nutku, Ferapontov, and Galvon. And they found for the simple eta two operators, one of third order, exactly of the form that we have seen in one slide before, and one of first order, which only apparently is more simple. Indeed, it's more complicated to find it. And both operators, it can be proved, they are completely determined by their leading coefficient matrix, which in the two cases, first order and third order, is given below in last line. So this is in the simple, for the simple eta, but we proved together with Jakub Vasicek that this is always the case. I mean, for generic eta, you can always find by Hamiltonian pair or this form. The only point is that the expression is quite involved unless you use a particular trick that we will see. Okay, so what is the invariance group of the problem? The point is that we found, together with Zhenya, Ferapontov, and Maxim Pavlov many years ago, that if you do a reciprocal projective transformation, you preserve the canonical form of the third order homogeneous operator. So what is a reciprocal transformation of projective type? It's a projective transformation of the dependent variables joined with a non-local transformation of the x. In this way, dx tilde is equal to delta dx, where delta is the denominator, the joint denominator of the projective transformation. So using this transformation, you can prove a lot of interesting things. And the most interesting thing is that the operator, which is determined by the leading coefficient matrix, here, for example, it's completely determined by this matrix, the third order operator. What happens is that that matrix determines an algebraic variety, which is called which is a quadratic line complex. For the first order operator, we have a much more limited understanding. In particular, we still haven't been able to associate to the first order operator any algebraic variety. We will later come back to this. So a bit of projective geometry. The viewpoint that we will use here was introduced by Sophus Lee. Basically, he used standard argument in projective geometry but in a, how to say, using not two distinct points to find a line in the projective space, but using one point and an infinitesimally close point. The displacement is dv from the point V. And then you see that if you consider the matrix of the two lines V and V plus dV, this matrix gives rise to the Plugger coordinates of the line passing through the 2 points, V and V plus dV. And the coordinates of this line are the so-called Plugger coordinates, and they have the particular realization as one forms of this type that you see here. So this V lambda dv mu minus V mu dv lambda. So they appear in papers of Sophus Lee, I think 1880 something. I call them Sophus Lee coordinates for Plugger embedding, because whenever you see a geometric object realized by these forms, you understand that you can interpret this object as some expression of Plugger coordinates. They indeed, if you do a linear transformation, projected transformation of the variables v1, v, and plus 1, you can see that these objects, p lambda mu, transform exactly like the Plugger coordinates, because the transformation is linear, so there is no difference between v lambda and dv mu in the transformation law. We regard the UI as an affine chart in PCm plus 1, so that UM plus 1 is 1 and DUM plus 1 is 0. So that these are the Lie coordinates in the affine chart. So the equation that is key to understanding that G3 is a Monge metric is the cyclic equation on which is part of the condition of Hamiltonianity of the operator A3. And this equation is known in the literature. It is basically a kind of differential geometric understanding of projective geometric variety, the particular variety in the space of lines, coming from some very old papers in the Soviet of the Soviet times. They were found by Evgeny Ferapotov many years ago. So whenever a metric fulfills this equation, it's a cyclic sum. This metric is called the Monge metric, and basically it can be arranged in the form of a quadratic expression of the one forms that I've shown you before. This quadratic expression in the last line of the slide, and so you can always find the matrix Q of constants, and these xt of x are just the one forms that I've shown you before. The quadratic expression in those one forms is a Monge metric, and it is a quadratic expression in Plugger coordinates. So it is a quadratic line complex. Of course, you have to intersect it with the variety of lines, which is the Grassmannian in the projective space of two forms of C n plus 1. Okay, but there is something more, because a third order operator is not just an arbitrary quadratic line complex, it's a very specific quadratic line complex. It's a quadratic line complex of rank n. And it has the following property. Basically, it factorizes into the product of two linear line congruencies. What is a linear line congruence? It's a linear expression that you see here below. Okay, this one, psi AB multiplied by PAB. This psi alpha is a constant, and psi alpha AB is a constant, are constants. So you have linear expression of of the Plugger variables, PAB. Note that A and B run from 1 to n plus 1, and alpha is an index which runs from 1 to n. So you have n linear expressions of Plugger coordinates. And what are these n linear expressions? Well, it was proved by independently by Doyle, who was a student of Peter Holder, and Potjomin and Balandin. Potjomin was a former student, has been a PhD student of Novikov. And it was proved that the metric of the third order homogeneous operator in canonical form, so when it is factorized, 1dx before, 1dx after, and one first order operator in the middle, can be in turn factorized as a kind of scalar product, because you see that phi is a proper scalar product with any signature. So it's a matrix of constants which is non-degenerate. And then psi alpha I is another matrix of which has the following expression. So it's a matrix of linear functions in the independent variables. It is symmetric in the lower indices. And this means that if you introduce projective coordinates, so if you reintroduce un plus 1, you can interpret this matrix as basically a one form in the projective space, so that you understand this expression as the kind of scalar product between one forms in the projective space. And these one forms, of course, are interpreted, as I told you, as indeed as Plugger coordinates. So the Plugger coordinates are minors of degree 2 in this case, and minors of degree 2 transforms like two forms. So I know that it's a bit involved, but this is how it is. And this means that we can regard them in a very simple way as a linear expression of the Plugger coordinates. Each of the two factors here, which is, okay, these are just the same factor repeated two times. So we have a linear line congruence whose square and scalar product is the quadratic line complex. Indeed, every quadratic line complex can be regarded as the square of a system of linear line complexes. One single equation is called linear line complex. N equation is a linear line congruence. So only when you have a linear line congruence, so when the dimension is right, you have a linear expression. You have a quadratic line complex which represents a Hamiltonian operator. So you have to play very careful with dimensions. So in other words, we can regard the operator as the span of a set of n two forms. And this gives rise to a third order operator with an additional condition. The additional condition that we derived so far in a paper with Zhenya Frevod and Maxime Pavlov is that, okay, you consider this scalar product between two forms and you just replace the tensor product with the wedge product. And in the end, you obtain a set of conditions, and this has to be zero in order for the operator to be a Hamiltonian operator. So it's interesting to observe that all scalar products which come from scalar product of the underlying space fulfill this condition. So it's kind of an integrality condition for the scalar product. But we didn't go very much into details of the algebraic properties of this form of the Hamiltonianity condition. Okay, so in coordinates, the condition of Hamiltonianity is amounts at these two cyclic conditions. Okay, but let us move to dimension, an example in dimension 4, which is very important because basically this is the first generic situation. So if you understand the WDV in this situation, you understand it in general. So what happens is that when capital N is equal to 4, you have 3 independent variables, of course, after T1. And then you have a set of 6 equations in general. Here we are using a very simplified form of eta, which has a parameter in the upper corner. I don't know if I wrote it down. Let me show you, but let me show you the, okay. So in case n equals 3, the parameter mu would be here in this upper corner. So it would be eta 1, 1 equals mu. And the same happens in n equals 4 in the example that I have shown you. It is an example which is more general than this one. And okay, it is present in the paper Geometry of 2D Quantum Field Theory, even if de Broglie wrote that there is no clear use of this particular metric in the context of topological quantum field theory, while there is a concrete use in enumerative geometry of this particular scalar product. We use that particular scalar product because it's very simple, but not the simplest one. And so we have 6 equations, so it's very highly of a determined system. What to do with it? Well, the point is that it can be solved with respect to x-free derivatives. And let me tell more. If you choose any independent variable, x, y, or z, you can solve it with respect to derivatives not contained in that independent variable. So this is a general feature. Then once you solve it, you find a minimal system in a sense, because you reduce the WDV equations from 6 equations to 4 equations. The other 2 vanish on account of these 4. So basically you are able to express these 4 variables, f, y, 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 f, y, y, z, f, y, z, z, and f, triple z, in terms of the other variables, and these are the expressions. We can use a classical terminology and say that we wrote the WDV system in orthonomic form. Then immediately one asks himself or herself if the system is passive, so if there are no hidden dependencies of derivatives of the system. And the answer is no. If you take cross derivatives, they will cancel. So the system is passive. So there are no further integrability conditions. And the point is that this holds for generic eta and the dimension n equals 4 and 5 for sure. I think that we did also computation in n equals 6. We have been able to prove something in this direction, but not to generalize completely this result. So if we consider the general WDV system, we can find in the general WDV system a subsystem which is linear with respect to TP free derivatives, where TP is the independent variable that you choose, whatever. So you can solve this linear subsystem, and then a subsystem which contains nonlinear equation with respect to TP free derivatives. And this subsystem can be killed. We saw it on computer and we verified it until n equals 5. The fact that the linear system can be instead uniquely solved with respect to TP-free derivatives is a general fact. So we can solve the subsystem. We do not know, we do not have a general result that says that all the other equations collapse. So let us go back to the system. So in particular, you see that if we choose x as the privileged independent variable, we see that the quadratic part of the quadratic equation in variables which do not contain x is exactly in the first equation the first two summands. And, you can select the first two equations and solve the others and replace into the first two, and the first two will vanish. This is what happens. Okay, so unfortunately, this result is only partly general, but we didn't manage to prove that the subsystem with possible nonlinearities vanishes upon the solution of linear part. But it is verified up to n equals 5. So we have an interesting theorem. If the conjecture is true, then WDV system in orthonomic form is passive for arbitrary n. And we have a general proof. But the point is that we have to know that the system is already solved. So it's in orthonomic form. Now, let us have a look at the compatibility relations. We constructed them exactly in the same way as in the n equals 3 case. So we have the first two sets of compatibility relations. They have a special meaning for us because to the right you have the x derivative. X is our privileged independent variable. So the first two, when restricted to the WDV equations, they become two commuting flows, and it can be relatively easily proved that these two systems are commuting. But this is a general fact. I mean that once you are sure that you can put the WDV system in orthonomic form, then you have commutativity of the hydrodynamic type systems in which you are able to transform the WDV equations. Moreover, this is completely equivalent to the passivity of the orthonomic system. So commutativity of the equations is the same as passivity. And it is true if you are able to reduce the system to orthonomic form. And the residual compatibility conditions, it can be verified that they all vanish. This is a theorem provided you already have proved the conjecture. Another thing that we do not know is if, solution of these two systems, a joint solution, can be transformed into a solution of the WDV system in the letter F. This is unknown, but it is very likely. Then let us see a construction, algebraic geometric construction by Jennifer Abondov and Sergei Agafonov many years ago. They associated with every system of conservation laws a certain variety, algebraic variety, which is called the congruence of lines. Again, it's a linear expression in Plücker coordinates, in some Plücker embedding of a certain projective space. What is the space? The space is the space of n plus 2 variables, homogeneous variables. So it is Pn plus 1. And the embedding is realized in the following way. You have the family of lines, which is described by n parameters, which are u1, un. The I are functions of those n parameters. And, and this expression defines a family of lines, which is n-dimensional. And it is a congruence of lines. The Plücker coordinates of the family are the expressions that you see below here. So ui vj minus uj vi, ui, vi, and 1. But what happens is that whenever you find a third order Hamiltonian operator, you to a certain first order system in evolutionary form, you know that the congruent the system is indeed a linear line congruence. So it's a linear expression of Plücker coordinates. So the fluxes in particular are given in this way. This psi alpha is the inverse matrix of psi alpha of the linear line congruence associated with the operator that we have already seen. Z alpha is a certain family of linear expressions. They have to fulfill this equation, and the associated congruence of line is here, and it is linear. So you can see that the first part is defined by the third order operator. And the last part is defined by the system of conservation laws. And so this is very important because basically what we are going to prove, what we are going to show you is that all WDV equations have this form. So basically all WDV equations can be arranged in the form of many Hamiltonian systems of the third order. And this is one of our main theorems. This is the structure theorem. We call it the structure theorem. So basically, if you fix two indices in the WDV equations, you are left with other two, and all the equations with arbitrary indices, two arbitrary indices and two fixed indices. Of course, we will have to fix an order because there are symmetries in these equations. They can be arranged in this form, as a linear expression of selected dependent variables and selected variables which will play the role of fluxes. So here there is complete description of coefficients. I don't want you to bother with this, but you can see that they are constructed starting only from eta. So basically we have nearly all ingredients for a third order operator, but let me remind you that the third order Hamiltonian operator, sorry, I have to go back, is the datum of, you see, there is phi, the scalar product, plus psi. So at the moment, we found only psi inside WDV. What I am going to show you is that there is also phi. Here there is the complete description, but it's too complicated. So you can see here, I highlighted in red the Plugger coordinates, in which a part of the WDV equations can be interpreted. So if you get the coefficients of these expressions, you find both the operator, the third order operator, and the system with one important detail missing still. So this is the scalar product phi. And this happens at every dimension for every choice of variables, always. And it's a theorem, it's not a conjecture. So, for example, let us have a look what happens in dimension 4. In dimension 4, you see that psi is, there are some matrices psi with upper index alpha, which is 0 in particular cases. In some other cases, is non-zero, and is constructed by means of the inverse of the matrix eta for an arbitrary eta. And this is another part of the Hamiltonian operator. It is the matrix of these omegas here. So we have a complete description. Then we have the metric theorem, what we call the metric theorem. So how to determine the scalar product? Well, we have to solve different equations that I have shown you before. And it can be seen that these equations are uniquely solved by the natural metric induced by eta on two folds. And it is this, the metric, contravariant metric. And this is quite a nice fact. We strongly suspect that there is some underlying geometric reason which we have been unable to find, unfortunately. We solved this system by an induction procedure, which meant finding the right order in which you grow the variables with the dimension. And after you find this, you have to find the right order in which to solve the equations. So basically, you solve first equations which are small and whose solution is clear, and then you replace into the others, and then you have to prove that everything vanishes once you find the solution for every coefficient phi. So you have to prove that all equations are fulfilled. And you prove this in the following order. First of all, the equation H1, then the equation H2 and the H3, which are basically the same, and then the equation H4, which is the hardest. And this gives you a picture of how the equations are solved. And you see that surprisingly, you obtain a natural metric for the two forms by which the operator, the third order operator, is made. And then you can extract a lot of Hamiltonian systems from every from the WDV equation in every dimension with arbitrary eta. This is one of our main results. The problem is how these systems relate with each other. Okay, if you are able to solve the congestion that I told you before, then you know that they are all commuting. Unfortunately, this conjecture is open. In high dimension, we don't know what happens. And even if for all that we could do, it was to compute by computer, and by computer, you see that it is always true. And the interesting thing is that all these computing systems have one and the same third-order Hamiltonian operator. Once you select the variable p, so you have that WDV equations in its first prolongation reduces to its equivalent to a family of commuting systems, where probably is still to be proved that solutions of the joint solutions of these systems can be regarded can define a solution of the proper WDV equations. There is a Baggetti correspondence. And then last slide about bihamiltonianity. So is it true or not that all these systems are bihamiltonian? The answer is we have no idea. The point is that we are able to find compatible first-order operators in all the known examples, known and computable examples. And recent results show that the operators have the form that you see here. So the metric of the operator in upper indices is determined by systems of the third order operator that we found so far, and that is compatible with G1. And the metric in coefficients incorporate also the part of the non-local part of the first order operator. Another result in this forthcoming paper by Lorenzoni, Opanasenko, and myself is that in the non-local case, the metric coefficient incorporates also the fluxes that appear, they are called the structural fluxes or structural flows. In the non-local part of the operator. And another result in our paper is that these fluxes are Hamiltonian systems of the third order operator. So you have zeta, alpha, j are families parameterized by j of Hamiltonian systems of the third order operator, plus you have additional Hamiltonian system of the third order operator. So the Hamiltonian systems of the third order operator completely determine the metric of a first order compatible operator, local or non-local. At least this is what comes out of our analysis in our forthcoming paper. The point is that we have not been able to prove by induction, for example, for the moment, that this happens for every dimension, for every metric eta. But for all examples that we know and we are capable of computing, we find that this is always present, the first order operator. So they are all bihamiltonian.
In the conjecture, you mean by every, you mean in any dimension?
In any dimension, in any capital N, for any capital N, all the commuting flows has the same bihamiltonian pair, same third order operator, same first order operator. This is the conjecture. And a last remark about invariance. So if you do a symmetry transformation of WDV, the systems remain bihamiltonian systems remain bihamiltonian in the same class. We still have no clear ideas how the system transformed. There was a paper by Mohofer-Strizhov about it, and probably the results can to some extent be generalized to cover the arbitrary n-dimensional case. And this is due to the fact that every linear transformation can be split as a composition of 2x2 transformation, and every 2x2 transformation is an invariance transformation of the bi-Hamiltonian pair. So this is the idea. Okay, we did a lot of computations. Okay, Stanislav computes with Maple, I compute with my own system, and sometimes we compute with, okay, we invert the roles, but I have a tested system since many years, and I still like to use it. We wrote a book, okay, with Joseph and Alec, okay, those who are interested can contact me, and you can give more details. And that's all. Thank you very much for listening to my talk, and thank you again for Joseph for your invitation.
Yeah, thanks, Raf. Quite interesting questions, remarks. Unfortunately, Zhenya could not attend the seminar. No question, no remark. Okay, Raf, thanks a lot, and I hope you will, well, sometime in the future we'll speak about this forthcoming preprint that you mentioned.
Yes, we are finishing it. We are improving our results, and
Yeah. Okay,
and
we'll
I
discuss
hope
it.
in not a
Raf,
long
and
time
please
to be available.
send, if you do not object, send your slides to Alec.
Okay, of course.
Thanks a lot. Okay, thanks you.
Thank you very
Thank
much.
you. Next time we meet, well, those who can personally at the independent university, and well, those who cannot are invited to Zoom. Goodbye and thanks a lot.
Bye-bye.